Okay, so ladies and gentlemen, welcome. So in today's video, we are going to look at the periodicity of the element. So what is periodicity of the element? So the periodicity of the element is refers to the recurrent trends. It refers to the recurrent trends in the properties of element as you move across the periodic table. So generally, we know that in periodic table we have a group and the period. The group is the vertical arrangement of the element, while the period is the horizontal arrangement of the element. So there are properties of the element that changes from top to the bottom or from right to the left. So those properties of the element that change down the group or across the period are called periodic properties of the element. So the periodicity of the element refers to the recurrent trend. So those recurrent trends in properties of the element as you move across the periodic table are called periodicity of the element, or we call them periodic properties of the element. So the properties of the element that changes down the group or across the period in the periodic table, they are called periodicity of the element. So these trends are as a result of the arrangement of electrons in atoms, which influences their chemical behavior. So generally, these properties of the element is due to the arrangement of the element. We know that naturally, or currently now we have over 118 elements on Earth, and these elements have different atomic number, and therefore they have also different arrangement. So the arrangement of electrons in an atoms is what actually influences the chemical behavior of the element. Like for example, the atomic number of sodium is different from the atomic number of magnesium. So therefore, their properties are not going to be the same because the arrangement of electrons in them are different. So understanding the periodicity is essential for predicting the properties of elements and their compounds. So let me just actually look at some of the properties. Let's assume this is a periodic table. Let's assume this is a periodic table. This one is periodic table. And we can see that from here, this one is actually indicates like the properties that changes or that changes across the periods, and these are the properties that also changes across the group. So we can see that here we have nuclear charge. So generally, as we can see, as you move down the group, the nuclear charges increases, the shielding properties also increases, the atomic radius increases, the ionic size increases, the ionization energy decreases, the electronegativity decreases. So it means that these are the properties that if you move down the group, as you go down to the group, these are how the traits, or these are how the properties of the element changes. Like for example, now when we said nuclear charge, look at it from the nuclear charge here, we can see that it increases down the group. Shielding effect is also increases down the group. Then we also have atomic radius, it increases down the group. Ionic size, ionic size also increases down the group. So you see all those in red color, it means that there are properties that increases down the group, while the one in blue, they are the properties that decreases down the group. So you see, assuming now in group one in periodic table, it started of course from sodium in group one, and it end with cesium. It ends with cesium. So no, it doesn't start with sodium. It started with hydrogen. So it started with hydrogen, lithium, sodium, potassium, francium, cesium. Yeah. So these are the elements that are in group 1. So you see, this means that from hydrogen down to the cesium, it means that the nuclear charges increases, shielding effect increases, atomic radius increases, ionic size increases from sodium to cesium. So it means that in group 1, if you ask which of the element has the highest nuclear charge, is cesium. And the element that has the lowest nuclear charge is hydrogen. And also for the shielding effects, as since we say it is also increasing down the group, it means that the cesium has the highest shielding effect. Why is it that, okay, as we are coming, let me just briefly explain the concept of shielding effect here. Remember in the element we have nucleus and a shell. So this is the nucleus. Let's say this is the nucleus, and then let's say we have two shells. So you see, generally there is an interaction between the nucleus and the outermost electron. There is an interaction between the nucleus. Let's say this is the nucleus, and then we have an outermost electron here. So there is always interaction between the nucleus and the outermost electron. So you see, as the number of shell increases, it means that there is a shield between the nucleus and the outermost electron. So assuming now let's say we have sodium. So sodium has how many shell? It has 3 shell. So you see, in the case of lithium, let's say lithium is also a member of group 1. So in the case of lithium, it has only 2 shell. So you see, so the shielding effect in lithium will not be the same with the shielding effect in sodium. So if we now increase another shell here, it means that there is 3 shells here. There are 3 shells. So meaning that there are 2 shells that shield the nucleus and the outermost electron. So it means that the more the number of shell increases, then the more the shielding effects. So that is why as you go down the group, the shielding effect increases. So that is actually the meaning of shielding effects. Then you see, so as you move across the period, look at what happened to the shielding effect. So you see, as you move across the period, because you have the same number of shells, let's say as you move from sodium in group 1, let's say this is group 1. So sorry, yeah, group 1, period 3. So as you move across the periods, then we have argon. So you see, in period 3, you have sodium. The next element is magnesium. Then the next one is aluminum, silicon. So as you move, in period 3, all the elements have the same number of shell. All the elements have the same number of shell. So therefore, their shielding effect remain constant. Their shielding effect remain constant because they maintain the same number of shell. So there is no any increase in a number of shell across a particular period. Let's say period 2, all elements in period 2 have 2 shells. So there is no increase or decrease in a number of shell. So that is why the shielding effect remain constant. So as we are doing the class, ladies and gentlemen, we will look at how these properties decreases and increases. But I think I can clearly say that from here, you see here, the nuclear charge increases. So I agree that the nuclear charge increases across the period. But here it's supposed to be decreased, not increase. Here it's supposed to be decreased. the nuclear charge decreases down the group and increase across the period. So let me also briefly talk about the nuclear charge here. So you see, when we said a nuclear charge is like an interaction between the nucleus and the outermost shell. So the more closer the element is with the outermost electron, then the more the effective nuclear charge. Like for example, in the case of hydrogen, it has only one shell. And in that one shell, there is one electron. And in the case of lithium, there are two shells. In the case of sodium, there are three shells. So now, and of course, at the center here, all at the center here, there is a nucleus. There is a nucleus. So one thing that I wanted to say here, and of course, there is an outermost electrons on each of these last shell. There is an outermost electron. So now what I'm going to say here is between the one with two shell, like in the case of lithium here, lithium, and the sodium, the one with three shell here, which one has, or which one is more closer to the nucleus? The lithium with only two shell, meaning that the distance between the nucleus and the outermost shell is very close, and that is why the effective nuclear charge in lithium is higher than that of sodium, and the effective nuclear charge of sodium is greater than that of potassium, because potassium it's also under group 1 with 4 shell. So it means that the more the distance from the nucleus to the outermost shell, the lower the effective nuclear charge. So that is why effective nuclear charge decreases down the group and increase across the periods. So it decreases down the group and increases across the period. So as we are doing the class, we will actually get to understand how these properties are. So the periodic table, uh, so you see here, we are going to look at the periodic table layout. So in the periodic table is organized into rows, that is period, and the columns, that is the groups. So you see these ones, from hydrogen down to francium, because francium is actually uh, is a radioactive element. So you see from hydrogen down to francium, they are all belong to group 1. So this is a column. So a column represent group of the element, while the rows, which is the period, reflects the period of the element. So you see now each period represent a new principal energy level. So you see hydrogen that has only one shell it means that it has one energy level. So you see, from hydrogen to helium, we have period 1, and from lithium to neon, we have period 2. So you see, the principal energy level increases because hydrogen has only period 1, so it has only one principal energy level. That is why it is in period 1. And lithium has two principal energy level. That is why it is in period 2. Sodium has three principal energy. So you see, each period represent a new principal energy level, while each group contain element with similar chemical properties. And that similar chemical properties is the electrons that are found on the outermost shell. So you see, beryllium, magnesium, and calcium, strontium, they are all in group 2. Why? Because they have two electrons on their outermost shell. From boron, aluminium, germanium, indium, all of them, they belong to group 3 because they have 2 electrons on their outermost shell. So you see, that is why if you ask to actually indicate the group to which an element belongs, then you draw the electronic configuration. So after drawing electronic configuration, the number of electrons on the outermost shell represent the group to which the element belongs, while the number of shell represent the periods to which that element belongs to. Then the layout of the periodic table reflects the periodic law, which said that the properties of elements are periodic functions of their atomic numbers. So you see, yeah, the periodic properties of the element are periodic properties of the element or are periodic functions of the atomic number. So you see, if element, the periods, the group which the element belong depend on its atomic numbers. So if an element has 5 shell, you dot 5. If an element has 6 electrons on its outermost shell, it means that that element belongs to group 6. If an element has 8 electrons on its outermost shell, it means that that element belongs to group 8. So you see that the properties of the element are periodic functions of their atomic number. So it's the atomic numbers that determine the properties of the element in the periodic table. Is the atomic numbers that you can use to indicate the group of the element, is the atomic numbers that you are going to use to indicate the group, as well as so many other properties of the element. So then the next thing, so as we said, atomic number. So atomic number, what is this atomic number? So atomic number of an element is the number of proton in its nucleus, and it determines the position of that element in the periodic table. So you see, and the number of protons in the nucleus of the atom is what actually determine the position of the element in the periodic table. Let me actually give a simple demonstration here. Let's say we have an element here like sodium. The atomic number of sodium is 11. So the first shell, sodium, will accommodate a maximum of 2 electrons. So here there are 2 electrons. And then the second shell, there are 8 electrons. And then the last one, there is 1 electron. So you see we have the first one contains 2. The second one contains 8. Then the last one contains 1. So you see, if we now say 2 plus 8, it will give us 10, and plus 1, it is going to give us 11. So that is actually the reflection of the atomic number of sodium here. So then now, from here, how do we actually determine the position of sodium and the atomic number? So this 1 electrons on the outermost shell indicate that the sodium is in group 3. This number of principal energy level, that is the number of shell, 1, 2, 3. It means that the sodium is in is in period 3. So then that is for the atomic number. Then atomic mass is the weight average of the masses of element isotopes, and varies also across the table. So you see, atomic number is the number of protons. So whenever you see atomic number, it means the protons of the element. And then the mass number is the sum of proton and the neutron. That is when you set Z, that is the atomic number, plus the neutrons number is what will give you the mass number of the element. So this is, whenever you see an element, you have this representation. So the number as a superscript, that is the number below here. It reflects that the number there is atomic number of the element, while the subscript, that is the upper number A here, represents the mass number of the element. So as you move from left to the right across periods, atomic number increases, leading to changes in elemental properties. Of course, that is it. So if you check group 1 or period 3, you see, as you move from left to the right, as you move from left to the right, the atomic number increase like sodium, magnesium, aluminum, silicon. So you see as you move across the period, you understand that the mass number increases. So then the next thing that we are going to look at is atomic radius. That's the trends in the atomic radius. So when we said atomic radius, what is atomic radius? So atomic radius refers to the size of an atom and generally decreases across a period due to increase in nuclear charge. So now, how? So simply, ladies and gentlemen, when we said atomic radius is the distance from the nucleus to the outermost shell. That is what you call atomic radius. Like for example, this is a shell and this is the nucleus. So if you have electron here, so the distance between the nucleus and the outermost shell is what we call atomic radius. Is what we call atomic radius. Like for example, let me show it like this. So you see from here to here is a radius. So that is why, because it is atom, and that is why it is called atomic radius. So the distance from the nucleus to the outermost shell is what you call atomic radius. And generally, this atomic radius decreases across the period due to increase in nuclear charge. So why do we have an increase in nuclear charge? Is because, ladies and gentlemen, you see here, let me set example with sodium here. The sodium has only one electrons on its outermost shell. Magnesium has two electrons on its outermost shell, while aluminum has three electrons on its outermost shell. So generally, ladies and gentlemen, as you increase the number of electrons on the same number of shell, because if you look at a course period 3, all the elements in period 3 has three shells. They have three shells. And of course, as you move across the period, the number of electrons on the outermost shell are increasing. Sodium has only one electron on the outermost shell. Magnesium has two electrons, while aluminum has three. So it means that the interaction between the nucleus and those two outermost electrons, it is increasing because the number of protons are increasing in the nucleus, while the number of electrons are increasing on the outermost shell. So therefore, the interaction increases. So as a result of increasing interaction between the nucleus and the outermost electrons due to increase in the number of electrons on the same number of shell, that is what leads to increase in effective nuclear charge. And that increase in nuclear charge tend to reduce the size of the electron. And that is why, so it tend to reduce the size of the atom. And that is why the atomic radius decreases across the period. While in contrast, atomic radius increases down a group as additional electron shells are added. So you see the atomic radius increases down the group, as you can see. Why? Because you are increasing number of shells as you move down the group. Like sodium here has only one shell. Lithium has two. Sodium has three shell. Potassium has four. Rubidium has five. Cesium has six, while francium has seven. So you see, as you move down the group, the number of shells are increasing while maintaining the same number of electrons. So that is why the atomic radius increases down the group. So understanding atomic radius is crucial for predicting how atoms will interact with one another. So now, let's look at the typical properties of this atomic radius. So you see, look at it. Sodium has lower atomic size. Lithium has, because it has two shells. Sodium has much more bigger than lithium because it has three shells. Potassium has much more bigger than rubidium. So you see, as you go down the group, because the number of shells are increasing, so that is why the size is also increasing. So therefore, atomic size increases down the group. and it decreases across the period, you see, because in the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, all of these atom has the same number. They has the same number of shell, but the number of electrons are increasing. So that increase in number of electrons on the same number of shell tend to cause an increase in effective nuclear charge. So then the next thing after atomic radius, ladies and gentlemen, I hope you understand the concept of atomic radius here. So the next thing is ionization energy. So what is ionization energy? Ionization energy is the energy that is required to remove an electron from an atom. So you see, generally, we have an element, some elements are metal while some are non-metal. So most of the electrons that have 1, 2, 3 electrons on their outermost shell, they are metal, while those that have 5, 6, 7 in their outermost shell, they are non-metal. So therefore, the more the number of electrons on the outermost shell, the more the energy that is required to remove that the outermost electron. So that is why when we said energy, ionization energy is the energy that is required to remove an electron from outermost shell. So ionization energy generally increases across a period because of increasing effective nuclear charge and stronger electron shell interaction. So you see, ladies and gentlemen, ionization energy is always increasing across the periods because there is an increase in effective nuclear charge and strong electron shell attraction. It means that there is a strong attraction between electron and the shell. So then down a group, as we move down the group, ionization energy decreases due to increased distance between the nucleus and the valence electrons. So ladies and gentlemen, simply here, we can now say that ionization energy is directly proportional to nuclear charge and inversely proportional to atomic radius. It means that the higher the effective nuclear charge, the higher the ionization energy, while the higher the ionization energy, then the uh the lower the atomic radius. So it means that the higher the atomic radius, the lower the ionization energy. So these two terms are very, very important to understand them. So ionization energy is directly proportional to nuclear charge and inversely proportional to atomic radius. So the higher the distance, the lower the ionization energy, while the higher the nuclear charge, the higher the ionization energy. So let's look at how this trends. You see, this is ionization energy, and of course, across or down the group. So you see here, it means that from here we can see clearly that the ionization energy of hydrogen is 2500, while the ionization energy of lithium is 2000. So as you move down, you see that the ionization energy of cesium is 0. So you see ionization energy is decreasing down the group while increasing across the periods. So now let's look at how these properties change with element. So you see, this is a typical examples of the phase ionization energy. So we said phase ionization energy, it means that is the energy required to remove first electrons on its outermost shell. So you see from here we can see that the ionization energy of sodium is lower than the ionization energy of helium. So as you can see clearly, ladies and gentlemen, from this, you can realize that the helium has the highest ionization energy than any other element. So you see, and then from helium, then lithium, then beryllium, and then boron. But now the question is, all these elements are in the same period. They are all in the same, no, okay, they are not all in the same period. Of course, if you can check from hydrogen to neon, they are in the same period. And from sodium, argon, they are all in the same period. So now let's take from hydrogen to neon. So you see, generally we say that ionization energy increases across the period. But now the question is, why is it that the ionization energy of beryllium here, sorry, boron, is lower than beryllium? That is the question now. Because if you say it increases across the period, so why is that the ionization energy? Because look at it, ionization in the beryllium is in the beryllium is in group 2, boron is in group 3. So you see, because beryllium come before boron. So why is it that the ionization energy of beryllium is higher than the ionization energy of boron? And also in the case of oxygen, why is it that the ionization energy of nitrogen is higher than the ionization energy of oxygen? So the answer is because of the half field configuration. So the half field configuration make the beryllium and the nitrogen to be more stable than that of boron and oxygen, and that is why the ionization energy of beryllium and boron is higher than that of, the ionization energy of beryllium is higher than that of boron, and also that of oxygen is higher than that of nitrogen. So this is also a similar examples that actually trying to show how the ionization energy increases and decreases. So, so then the next thing is electronegativity and the trends. So what is electronegativity? So when we said electronegativity, ladies and gentlemen, electronegativity is a measure of an atom's ability to attract and bond with electrons. So this property tends to increase across a period and decrease down a groove. So before actually we talk about the trends, what is electronegativity? So generally, electronegativity is the ability of the element to attract electron toward itself. So most of the non-metals, they are electronegative element and have the ability to gain an electron from metal atom. So the ability of the element to attract and bond with electron is what we call electronegativity. So these properties tend to increase across the period and decrease down the road. So the trend in electronegativity helps explain the nature of bond formed between different elements. And that is what we have some of the elements that we call them the most electronegative element. The most electronegative element in periodic table is fluorine, followed by oxygen, and then nitrogen. They are the most electronegative element in periodic table. So let's look at some exercise here. Look at the measure of an atom's ability to attract electrons. A chemical bond is called electronegativity. So the answer is electronegativity. And then which of the following bond is least polar? So as I just mentioned, the electronegativity of fluorine is the most electronegative, followed by oxygen, then nitrogen, and boron. And then the one with the least electronegativity is hydrogen. So that is why they are least polar. They are least polar. So what are the metallic properties of the element, metallic and non-metallic? So elements exhibit varying degrees of metallic and non-metallic character. So based on their position in the periodic table. So metallic character increases down a group and decreases across a period from left to right. So generally, as you go down the group, the number of shell increases. And the more the number of shell increases, it means that the more the chances an element has to release. So as we actually move down from uh, from top to the bottom, the metallic character increases. That is, it increases down a groove and decreases across the period. So therefore, ladies and gentlemen, as we go down the groove, the distance between the nucleus and the outermost shell increases. So as a result of that, there is a decrease in effective nuclear charge, indicating that the element can easily loses its outermost electron, and it is decreases across the period from left to the right because of an increase in effective nuclear charge. So effective nuclear charge is a key in metallic characters of the element. So understanding this trend is essential in predicting the behavior of elements in chemical reaction. So, ladies and gentlemen, I think without wasting much of our time, let's look at the role of electronic configuration. So electronic configuration describes the arrangement of elements in an atomic orbitals. So the periodicity of element can be explained through similarities in electronic configuration among elements in the same group. And that is why we said elements that have the same electrons on their outermost shell indicate that the element belongs to the same group. And those that have the same number of shell indicates that the elements are in the same period. So knowledge of electronic configuration aids in predicting the chemical reactivity and bonding behavior. So ladies and gentlemen, without wasting much of our time, we are going to stop here. And if this is the first time you are coming to this of my YouTube channel, please try to subscribe and join the YouTube community. Thank you very much and see you next time.